Hello, in this video let's continue with the discussion on the frequency response of amplifiers. So we'll look at a few more examples of the common source, I'll look at a couple more techniques, and then we'll continue with looking at the next two configurations, which is the common gate and the common drain or the source follower. Now we've looked at different techniques to find the frequency response of amplifiers. So the dominant pole, I just wanted to cover how do you do the dominant pole, or how do you find the dominant pole in a common source amplifier, right? So let's use the open time constant technique. I mentioned that in the previous video, but I'd like to work it out with you in this video. So again, here is a common source amplifier. You have a signal source with a resistance Rs, a load resistance Rd, and a load capacitance of Cl. Right. So if I look at the small signal equivalent of the circuit, the small signal equivalent looks like this. There is a CGD between the gate and drain, a CGS between the gate and source, and you have RD, which I will call out RD prime, which is nothing but RO will fall across RD, so I'll call RD parallel RO as RD prime. And similarly CDB, which is the load component of this capacitance, that will fall in parallel with CL, and so we'll call CL prime as some CL plus CDB. Right? So now let's use the open time constant technique to find the dominant pole. So let's recall what the open time constant technique is. You take with each capacitor one at a time, you open circuit the capacitor, remove all of the capacitors in the circuit and find the Thevenin resistance across the capacitor, and then the time constant associated with that capacitor is going to be its Thevenin resistance times its capacitance. You do that for all the capacitors in the circuit, sum of the time constants, and the reciprocal of that time constant gives you the dominant pole of the circuit. Right? So let's start with CGS. Now if I look at CGS, the open circuit CGS, I've removed CGD and CL from the picture. Then essentially the rest of the circuit I don't care. So the equivalent circuit for CGS, I'm shorting the input signal, and what I have is essentially Rs. So for CGS, the Thevenin resistance is Rs, which means that the time constant for CGS alone is going to be Rs times CGS. Now let's look at the other simple one, which is the CL prime. So again, if I look at CL prime now, all I'm going to do is again short the input, remove all of the capacitors in the circuit. And so when I do that, I essentially have a common source amplifier whose input is also grounded, right? And so therefore VGS is 0. So GM-VGS disappears, and all I'm left with is RD prime, and so RTH is RD prime, and the time constant associated with CL prime is going to be RD times CL prime. The last and the most interesting one is what happens to CGD, again because CGD falls across the input and the output nodes of the circuit. So now let's look at the equivalent circuit here. Again, I remove the capacitances, and what I have is right here. So I want to find the Thevenin resistance between nodes A and B. Right? And so B is connected via Rs to ground, and A is connected through GM, VGS and RD. And this VGS is now the voltage drop across Rs. Right? And so VGS is not 0 in this case. I just want to be careful, because the way you do a Thevenin resistance is you're going to apply a voltage across AB, and you're going to measure the current flowing through from A to B. And then the VAB by IAB is going to give you the Thevenin resistance. So let's look at the voltage across Rs. So if I have IAB flowing through this, IAB is going to divide itself across GM, VGS and RD prime, flow through ground, and then come up from ground through Rs back to B. Right? So if you look at VGS, my VGS is given by minus IAB times Rs, because IAB is flowing from ground into node B. Similarly, if I look at the voltage between A and ground, the voltage at A is given by the voltage across Rs, which is VGS, plus VAB. So if I look at VA, which is the voltage across RD prime, VA is going to be given by VAB plus VGS, right? And so therefore, if I now look at the current in RD now, again remember IAB is flowing in, GM-VGS flows through this branch, so the remaining current flows through RD prime. So current flowing through RD prime is IAB minus GM-VGS, and if I substitute the value of VGS in, I'm going to get IAB into 1 plus GMRS. And so therefore, I put that back into this equation because I know what the voltage across RD prime is. So I get IAB into 1 plus GMRS into RD prime should be VAB minus IAB RS because VGS is minus IAB RS. So here it's one equation which has VAB and IAB. So therefore I can find the Thevenin resistance of ratio of VAB and IAB. As interest is given by RS plus RD prime plus GM RS RD prime, right? So again, this is not a trivial case. You can't just look at the circuit and write this down. It helps for the first few times to do the entire Thevenin analysis. And so therefore, if you look at the time constant associated with CGD, it's going to be given by tau 2 CGD. Again, I collect the like terms, so I'm going to have RD prime plus 1 plus GM RD prime times RS. Right? And so now if I look at the dominant pole for this common source amplifier, my tau 1 is given, which is the time constant associated with CGS, is RS CGS. This is the time constant associated with CGD, and this is the time constant associated with CL prime. And so if I look at the dominant pole, the total time constant is essentially going to be the sum of these three time constants. And as expected, this is the coefficient of S in the denominator of H of S when we did the exact analysis. So if you look at that video, you'll see that this is exactly the coefficient of S in the denominator, which is what is expected because in the dominant pole, you assume there's one pole, and so you approximate B1 to be 1 by omega, right? And so therefore the omega, the dominant pole or the 3 dB frequency of this particular amplifier can be written as the reciprocal of this tau H, which is omega 3 dB, which is given by 1 by this expression. Okay. Now let's talk about another figure of merit of a MOSFET, and that's known as a unity gain frequency, right? Now, why is this important? So the higher the unity gain frequency, the better the MOSFET is at amplification. So as you've seen, if you look at the common source amplifier, what's happening to common source amplifier is that as the frequency of the signal increases, I see the gain drop, right? So if I want to compare two technologies, for example, and if I want an operation for some certain megahertz or gigahertz signal, and if I want a certain gain, right, I'm going to pick a technology, I'm going to pick the transistor which gives me better performance at that particular frequency, right? And so if a transistor is able to perform for a wider band of frequencies, I will choose that over something which performs on a narrow band. And so to understand what is the widest band that can be associated with the MOSFET, we talk about this figure of merit, which is known as the unity gain frequency, and is defined as the frequency at which the short circuit current gain of the MOSFET in a common source configuration becomes unity. Right? And why is unity important? Because if you look at log of 1, it's 0. So that is the point where the Bode plot essentially goes to 0 on the y-axis. So here I'm looking at the common source amplifier. So this is my common source amplifier model. I have a load RD, signal source RS. Again, I'm assuming R0 is not present, or if R0 is present, I'll lump it into RD. What I want to do is so I'm going to apply an input current. So remember, because there are capacitances here, we're considering capacitances, I can send in currents now. It's not like the mid-band analysis which we did prior to doing frequency analysis, where we assume the gate to be essentially an open circuit. The gate is actually capacitive. And so I have a short circuit output here, which is I out. So the unity gain is going to be defined at for the frequency at which this I out by II is 1, right? So now let's find out the gain between I out and II. So if I write II, that is the input current. The input current is given by the current flowing through CGS and the current flowing through CGD, right? And if I assume that the voltage drop across VGS is across CGS is VGS, remember CGD is also connected between this point and the other point, and this other point is grounded. So the voltage drop across CGD is also VGS, and so therefore my net current flowing in is going to be given by current in CGS and the current in CGD, both of which are S times VGS into CGS plus CGD. And then I have this current which is coming out of CGD, that's going to flow through GMVGS and RD and I out, right? So if I look at this node, current flowing from CGD plus I0 is going to come in, and both of them are going to flow through GMVGS and RD. Now RD is connected between two ground signals, so no current flows through RD. So what I have is SCGD VGS, that is the current flowing in CGD, plus I naught should be equal to GM VGS. So here I get another expression for I naught in terms of VGS. And so therefore I can talk about the gain between I naught and II as GM minus SCGD divided by S times CGS plus CGD. Right? And again, if you look at this, you have a zero, left hand zero, and you have a pole at the origin. Right? Now, if I look at sinusoidal excitation, that is when S is equal to j omega, then my I naught by II can be written in this format. And if I look at the magnitude of this gain, it's given by Gm by omega into CGS plus CGD times square root of 1 plus omega squared CGD squared by Gm squared. Now we'll make a simplifying approximation here that we'll say for most frequency of interest, this number that we have next to 1 is a small number, right? Because CGD is a small number, omega CGD is smaller than Gm. And so when you use the approximation, my I naught by II drops to a very simple expression of Gm by omega into CGS plus CGD. And so therefore the unity gain frequency, which is known as omega t, is given by when this magnitude goes to 1, which is given by Gm by CGS plus CGD. And so you'll see that this feature will come across many times. In most modern transistors, CGD is much smaller than CGS, especially in saturation. And so many a times you'll sometimes see that this is approximated to even Gm by CGS. Now, let's do another example before we go to common gate. Let's find the transfer function of this circuit. So let's first understand what this circuit is. This circuit is a common source amplifier again, but in this case, both the transistors are doing the transconductance, right? So this is an inverter. If you look at initial logic, when both are in saturation, it's going to give a very high gain because both the P and the NMOS are amplifying. If I look at the capacitors in this, I have multiple capacitors. I have CGS N between the gate of the NMOS and ground, CGD between the gate and the drain of the NMOS. Similarly, I have CGD-P between the gate and the drain of the PMOS. The gate of the PMOS is connected to CGS-P to ground, and then load is the sum of the two drain capacitances. Now, I know how to do the transfer function of a common source amplifier. So if I'm somehow able to convert this to a single transistor common source amplifier, then I can write out the transfer function easily, right? So what I'm going to do is I'm going to try and see what would be the equivalent circuit, if you will, for a single transistor, right? So if I'm going to convert that to a single transistor, that transistor is going to have an effective transconductance of Gm effective given by the sum of Gmn and Gmp because both transistors are transconducting. Similarly, the effective Rout of the circuit is Ron parallel Rop, and so therefore the midband gain, as we have calculated before, is going to be given by Gmn plus Gmp into Ron parallel Rop. Now if I look at the capacitances, right, CGS of N and CGS of P both fall from the input node of the amplifier to signal ground. Similarly, CGD2 and CGDN and CGDP both exist between the amplifier input and the amplifier output. And similarly, CDBs of both are exactly only at the output. So I can talk about the effective CGS as given by CGSN plus CGSP. Similarly, a CGD effective as the sum of the two CGDs and the load capacitance as the sum of the two CDPs, right? So I have all the capacitances, I have the effective GM, I have the effective Rout, right? And so once I know all this, basically I go and plug these values back into the transfer function that we calculated for the common source, and that would give you the transfer function for this particular circuit. Okay, all right. So let's switch gears and talk about the common gate amplifier. So to remember, the common gate amplifier, the input is given at the source of the transistor, the gate is biased, and the output is pulled from the drain of the transistor. So let's keep it simple now and say suppose lambda is equal to 0. And let's say I've used a coupling capacitor. So we look at the low frequency side of things first. So if I have a coupling capacitor at the input, right, what happens to the amplifier, right? So what's going to happen therefore is the effective impedance at the input of the amplifier has changed, right? Because instead of RS, I now have an RS and CI in series. And so if I talk about the transfer function, all I have to do is, instead of using RD by 1 by Gm plus RS, this RS I'm going to represent it by its impedance, which is actually RS plus 1 by SCI, right? This is the net impedance I've applied at the input, right? And so when I solve and recollect terms, I'm going to get H of S as SRDCI by SCI into 1 by GM plus RS plus 1, right? And so what you see again is like the common source amplifier, there is a 0 at 0 and a pole at 1 by Ci into 1 by Gm plus Rs, right? So that's going to be your low frequency part of the analysis, right? Now let's see what happens at high frequency. Again, we start with this common gate amplifier and let's look at all the capacitances, transistor capacitances. So at the input node, I have a CSB connected from the input to ground. My CGS is connected from the input to the gate, and this gate is signal ground. So CGS also builds in as the input. Similarly, CGD on the other hand is connected with the output node and the gate is again signal ground. So CGD builds as an output capacitance. CDB also builds as an output capacitance. So in this common gate configuration, what you see is there is no capacitance that is connected between the input and the output, and primarily because of the fact that the common gate, we connect the input output to the source and drain of the transistor, and in a MOSFET the source and drain are assumed to be intrinsically electrically disconnected, right? So there is no capacitance. If there was a capacitance between source and drain, we would have caused Dibble, right? So the whole point of an ideal transistor is you want to ensure that the drain voltage does not affect the source voltage, right? And so therefore what happens is you don't have a capacitance connected between input output, which means the Miller effect doesn't work here. So you see that because of that, there are no high capacitances which come in. Remember, these capacitances are smaller. In CS, what happens is that CGD gets amplified because of GMRD and falls at the input, pulling in the input pole. However, here we don't have that effect. So therefore, what happens in the common gate amplifier, generally you see that the amplifier works at high frequencies, right? So it is used for bandwidth extension, right? So we can analyze the circuit simply as an input pole and an output pole. Now again, if lambda is equal to 0, my midband gain is GMRD, positive. And if I look at the total capacitance at the input, the total capacitance at the input is given by CSB plus CGS. The total capacitance at the output is given by CGD plus CDB. Right? Similarly, if you look at Rn at the input, the Rn at the input is going to be given by Rs. Remember, when you're doing Rn, this Vi is grounded. Your input, remember the Rin of the common gate is 1 by Gm. So your Rin is actually Rs parallel 1 by Gm. Your Rout is Rd, and so therefore the poles are given by the input pole is given by 1 by Rin, which is Rs parallel 1 by Gm, times the total input capacitance, which is CGS plus CSB. And similarly, the output pole is given by Rd into CGS plus, this should read CGD plus CDB. Right? And so therefore I have the two poles, and so my H of S is given by Am divided by 1 by 1 plus S by omega P in, 1 plus S by omega P out. Now let's do a couple of examples. So you're asked to find the poles of the circuit, lambdas are 0 again. So again, first thing is you see that this is a common gate amplifier because the input is applied at the source, output is pulled at the drain. So the way we've analyzed common source amplifiers, let's first look at all the capacitances in the circuit. Right, so every transistor will have a CSB, a CGS, a CGD, a CDB, similarly CGD, CGS and CDB. Now CGD2, if you look at M2 here, CGD2 is connected between two nodes which are shorted. So CGD2 is essentially bypassed. You don't have to worry about CGD2. So if I look at the total input capacitance again, the total input capacitance is going to be CSB1 plus CGS1. Right? There's no change in that compared to the previous. However, if you look at the output capacitance now, it's going to be CGD1 plus CDB2 plus CDB1 plus the same node is shown up here at the gate of the NMOS there, the PMOS, and so that's going to be CGS2. So your total output capacitance gone up by CDB1, CGD1, CDB2 and CGS2. And so again, Rn remains the same, Rs parallel 1 by Gm. Now Rout, you're going to look down and up. Now because lambda 0, looking down into the transistor is essentially infinity. Looking up, again lambda 0, and so looking up you're going to see 1 by Gm2. So the Rout has gone down to 1 by Gm2 from the previous case, and its capacitance also has gone up. So this circuit is going to pull in the output pole. And so if we look at the input pole is going to remain the same as previous. 1 by RS parallel 1 by GM, CGS 1 plus CGS 1. And the output pole is now going to be much smaller, and it's given by 1 by GM2 into 1 by CGD1 plus CDB1 and so on, right? So that's going to be the way you'd analyze the poles for the circuit. So you can also use the dominant pole technique for the common gate amplifier, and let's look at that quickly. So again, I have these, if you look at the common gate, I have CDB, CGS, CGD. Let's first start with then lambda 0. Then for CGS, as we said, the RTH is RS parallel 1 by GM, and so tau 1 is going to be RS parallel 1 by GM times CGS. I've neglected CSB for just because it's normally a small number. Similarly, if you look at the output I have three capacitors, CGD, CDB and CL. So the net capacitance of the output is larger and its Thevenin is RD, and so therefore tau 2 is given by the capacitance term RD. And so therefore the dominant pole, all I do is take the reciprocal of tau 1 plus tau 2, because there are only two capacitors here, and so that's my dominant pole, which is going to be the sum of the two time constants. Now when lambda is not equal to 0, again you know how to analyze the circuit. When lambda is not equal to 0, what happens is the input and output are connected via R0, and so therefore the input resistance, instead of it being 1 by GM, now becomes RD plus R0 divided by 1 plus GM R0, right? Similarly, the output, I now, when I look down here, I'm not going to see infinity, I'm going to see RS through this capacitor, through this transistor. So it's going to be GM R0 into RS approximately. So looking down, I have GM R0 RS, looking up, I have RD. So my R out changes to RD parallel GM R0 RS. And again, the rest of it remains the same. Find tau 1 using this R in, find tau 2 using this R out, and then the dominant pole can be done by 1 by tau 1 plus tau 2. So the dominant pole technique is a very quick, easy technique and generally gives you a handle as to what the 3 dB frequency is. And fortunately for us, simple circuits tend to have one dominant pole, so this kind of works. As we looked at previously, when the poles are close enough, then the dominant pole fails. But when you have one pole which is generally smaller than everybody else, this technique works very well. Now let's look at the source follower. Now the source follower, if you remember, the input is given at the gate, the output is pulled from the source of the transistor. So this is my load RL, I have CL. So let's draw the equivalent circuit first. So I have a CGS between input and output. So here in the source follower, now the CGS works like the Miller capacitance, right? Because you now have it falling between the input and output. But the advantage of the source follower is that because the gain of the source follower is generally 1 or less than 1, the Miller effect is not that prominent. In the common source, that stage is used for high gain stages. So it has a high gain which leads therefore for the Miller effect to be pronounced. Here CGS has a minor effect because the gain of the circuit is less. CGD on the other hand falls like an input capacitance. CDB is not in the picture because it is bypassed. And similarly CSB falls at the output node of the circuit, right? So if I now look at its equivalent circuit, I have a CGS, a CGD and a CL prime if I will. Let's assume R0 is present. So let's solve the circuit. So first thing is, you know that Vn is written as the voltage across R sig plus the voltage at this node. So if I call this node Vg, then In R sig into V plus Vg is the total input voltage. Vg is given by Vgs plus V out. Again, this is similar to what we've done when we did the source follower analysis. And the In is given by the current flowing in CGS, current flowing in CGD, which is SCGD Vg, because Vg is the voltage drop across CGD. VGS is the voltage drop across CGS. So this is my In. And so therefore I can write my Vin in terms of VGS and V out as the following expression, right? Now I apply KCL at the output node here, and what I have at the output node is total incoming current is SCGS VGS, that is through the CGS, plus GM VGS should be equal to the current flowing out through RL and R0. So again RL prime I've taken to be RL and R0 because These two are essentially parallel to each other. And then I have an current flowing through the load capacitance, which is SCL V naught. So again, I have two equations between V in, V out, and VGS. So I can eliminate VGS from one and find the gain. So we'll do precisely that. VGS can therefore be written as V naught into SCL plus so by this. Substituting that back into the V in expression, you get an expression of V naught by V in as this expression here. So it's SCGS plus GM divided by a second order polynomial, right? And so what you see therefore is, if I collect the terms, I'm going to get GMRL by 1 plus GMRL. Now this is the midband gain. And you get 1, 0 and 2 poles, right? And so the interesting thing here is that the 0 is on the left hand plane, right? So this is minus GM by CGS, it's a left hand plane 0. And then you're going to get 2 poles on the from the denominator. Now let's look at a simple source follower where I'll make some approximations where I'll say RL is infinity, lambda 0, CL is 0. Right? So we are purely looking at the impact on the device capacitance. Now an interesting thing happens here. If I go back and substitute for the values of B1 and B2, I get B1 to be this and B2 to be this. And when I put it in denominator expression, the denominator factorizes out as 1 plus S R6 CGD into 1 plus S CGS by GM, right? And now if I look at H of S now goes as this divided by this. Again, in this case when RL is infinity, your midband gain is 1. So what you have is H of S is 1 by 1 plus S CGD R6. So the interesting thing happens here is because of the fact that the gain is 1, CGS no longer comes into the picture. All we are left at is a single pole circuit determined purely by the input node, right? CGS gets shorted, and the reason is because your V out is now following V in. So because of that, what happens is we say CGS is bootstrapped because the two plates, if you will, of the capacitor are both moving in the same direction, right? And therefore that does not contribute to the frequency response. So you're essentially left with the frequency response determined purely by the input node of the circuit. Again, the output node CL is infinity and CL is 0, so you don't have an output pole. So a couple of notes on the source follower. The circuit has 3 caps, transfer functions of second order, right? And remember that it's very different from what we've seen before. The transmission 0 is at a frequency slightly higher than unity gain, so it's a very, very large 0. So normally it doesn't affect when we're looking at operation of the amplifier in regular regimes. Now, this is a second order system. We'll see that this source follower is used a lot in oscillators, etc. So we sometimes like to refer to this from its the signals and systems scenario from a pole and its quality factor. So I can rewrite the denominator expression as 1 plus 1 by Q into S by omega naught plus S squared by omega naught squared, where omega naught is 1 by square root of B2 and Q is square root of B2 by B1. Now this is used especially when you're doing filter design, etc. And if you look at the roots are given very simply by this omega naught and Q factor. And what happens is you see that the higher the value of Q, the closer the poles get to the imaginary axis. Therefore, this Q is known as a pole quality factor. And for most cases, when we use Q is greater than 0.5, the poles are complex conjugates. And what is interestingly seen is when Q is equal to 0.707, these poles are exactly 45 degrees away from the real axis. Now, why is this important? Is because if you look at H of j omega, right, for a second order system, what happens is you see that the H of j omega as a function of Q, you see an interesting thing happen. As Q increases from 0.5 towards 1, you start to see that the H of S no longer remains like a flat function, it starts to exhibit a peak, right? And this is where you start getting the band pass kind of effect. So this is a second order system which gives a band pass effect, primarily because of these two complex conjugate poles as they begin to move closer to the imaginary axis. And this 0.007 is an limiting case, and it's that point, Q point, at which we say that this function is maximally flat. So that is going to be the last point at which the function doesn't have a peak, after which you're essentially going to see the function show a peak as your Q factor increases. Now let's look at the input impedance of the source follower, right? So if you look at the input impedance of the source follower, again, we'll replace the transistor with a small signal circuit, assume lambda is equal to 0 in this case. This is a ideal current source, so there's no load resistance. And if you neglect CGD for now, as I said, suppose CGD is small, what you see is you see Vin given by VGS plus In plus GMVGS into SCL, right? So this is going to be VGS plus whatever is the voltage drop across CL. This is essentially your I out or V out. And therefore I can write my Vin as In by SCGS plus In by SCL plus GM squared In by S squared CGS CL, right? Or in other words, your Zin is 1 by SCGS plus 1 by SCL plus GM by S squared CGS CL. Now why is that important? If you look at sinusoidal excitation and S is j omega, Zn of j omega becomes 1 by j omega into this minus gm squared by omega squared CGCL. So what you see here is high frequencies, the real part of the impedance becomes negative. So what we're getting is a negative resistance effect. And it's purely happening in the source follower, right? Purely coming from the fact of this S squared that is coming in into the source follower. So this gives you interesting possibilities when you start looking at design of oscillators, etc. Similarly, let's look at the output impedance of the source follower. Again, it gives you some interesting insights. For the output impedance, I short the input and I measure IV out by I out, right? So again, here I have SCGS VGS plus GMVGS plus I naught. So if I naught is coming in, GMVGS is also coming in. SCGS VGS is the current flowing in. So at KCL at this point gives the sum of the three currents to be 0, which gives you I naught as minus GM plus SCGS into VGS. Similarly, if I apply KVL in this large loop, I'm going to get V naught as 1 plus SCGS RS into VGS. And so therefore Z naught becomes V naught by I naught, which is 1 plus SCGS RS by GM plus SCGS. Right? Now let's look at how this function looks like. Now when at low frequencies, right, when j omega is very small, this looks like 1 by GM, which is what we know, right? In the midband, we see that the source follower, we use it to get a small output resistance. It's normally used as the last stage of a voltage amplifier. So your Z naught is 1 by GM at low frequencies. At high frequencies, when S tends to infinity, you get Z naught as RS. Now typically when we use source followers, right, we use source followers to transform the output resistance. So normally the input resistance of the source follower is higher. So let's look at a case where 1 by GM is less than RS, right? So when 1 by GM is less than RS, now if I plot Z naught as a function of omega, what I see is interesting. I see that the Z naught, as my frequency increases, my output impedance increases with frequency from 1 by GM to RS. So I have an output impedance, or I have a circuit who, if I look at its output, has an impedance increasing with frequency. Or it is an output which looks inductive, because in an inductor, the impedance increases with frequency. So here what you've done is you've simulated an inductor, if you will, using just the transistor and the capacitor, right? And again, this is a very important circuit in oscillators, and the output impedance increases with increased frequency. So we model the output sometimes as this fashion, where you have R1, R2, and you have an inductance L, right? Now again, at omega equal to 0, this going to become to infinity, so I'm going to have, at omega equal to 0, this L is shorted, so essentially my Z out is R2, so my R2 is 1 by GM. When it's at infinity, my inductor gets open circuited, so I have R1 plus R2, and that is RS, which gives me R1 as RS minus 1 by GM, right? Now if I want to calculate the effective impedance, all I do is I say R1 parallel SL should be Z0 minus R2, right? Because R2 plus R1 parallel SL is the effective impedance. And this Z naught we just calculated is given by 1 plus S CGS RGS by this. R2 we said is 1 by GM, right, which falls in this format. And so therefore if I say 1 by R1 plus 1 by SL, right, which if I take the reciprocals of both the left hand and right hand sides, I get this expression, on which case I get the effective inductance of this circuit. So remember, this is simulating an inductance. This inductance simulated is proportional to CGS, inversely proportional to GM, and driven by this expression Rs minus 1 by GM. So the source follower is interesting from the point of view that it not only finds uses as an output stage, it finds uses in a lot of these other circuits which basically utilize its property of either negative resistance or its inductive properties to create interesting circuits.